So, let's go. You're looking at the most important scientific survey of the last decade, and almost nobody covered it. In 24-25, researchers asked over 1,700 scientists a simple question. Do you think alien life exists? The answer should have been front page news. It wasn't. And buried inside that answer is something even weirder, a gap between what experts actually believe and what the public thinks they believe. So large it has a name. We'll get to that. But first, 10 scenarios where the math, the missions, and the live arguments between actual scientists all point the same direction. Number 1. The survey nobody talked about. Here's the setup. Most people assume scientists are cautious on aliens, politely skeptical, professionally non-committal. That's the image. The reality, as of 2025, is different. When researchers surveyed over 1,700 scientists, astrobiologists, and non-astrobiologists, the results on basic microbial life were essentially unanimous. Not majority, not strong consensus, near unanimous. The scientific community, quietly, without a press conference, has basically agreed that simple alien life almost certainly exists somewhere in the universe. On intelligent life, 58% of astrobiologists said it likely exists. That's not a fringe position. That's a majority. Now here's the part that should bother you. A separate survey of highly educated, scientifically engaged people, the kind of people who watch videos like this, found that 95% of them personally believe alien life exists. But most of them thought only about 12% of experts agreed with them. They were off by 46 percentage points, almost half a survey. Scientists call this pluralistic ignorance. The researchers who found it called it the cosmic closet. The public and the scientific community have been in quiet agreement for years, each assuming the other side thought it was crazy. So before we get into the evidence, the oceans, the signals, the structures, the math, just know that the experts are already on board. The question now is, what kind? Number 2, the ocean literally next door. You probably think the search for alien life is about telescopes pointing at distant stars. It's not. Some of it is happening in our own backyard right now. On moons, you could theoretically see on a clear night with a decent pair of binoculars. There are at least 5 confirmed liquid water oceans in our solar system. Not ancient, not theoretical. Confirmed, right now, liquid water. Europa, orbiting Jupiter, Enceladus, Titan, Ganymede, and Dione, orbiting Saturn. Possibly more. When scientists say confirmed, they mean spacecraft went there and measured it. Enceladus is the one that keeps people up at night. It's a moon about the size of the United Kingdom, small enough that its gravity is only 11% of Earth's. And it has a global ocean, at least 10 kilometers deep under a shell of ice. Maybe much more. What feeds it is tidal heating. Saturn's gravity needs the moon like dough, generating heat, keeping the water liquid in a place that should be frozen solid. Here's where it gets strange. At the south pole of Enceladus, there are cracks in the ice called tiger stripes. And through those cracks, the ocean is shooting water 500 kilometers into space. Not a trickle. Geysers. Enormous geysers, constantly firing, feeding an entire ring of Saturn, the E-ring, with ocean water from a moon. If anything lives in that ocean, it's already being broadcast into space. The Cassini spacecraft flew through those plumes. Directly through them. It tasted the ocean from orbit. What it found? Liquid water, salt, complex organic molecules, silica nanoparticles that only form near hydrothermal vents, and hydrogen gas. That last one matters enormously. On Earth, deep ocean hydrothermal vents use a chemical process called serpentinization, rock reacting with water, releasing hydrogen. That hydrogen feeds entire ecosystems of bacteria that never see sunlight, never need it. They eat chemistry, and Enceladus has that chemistry running right now. There's a problem Cassini couldn't solve. The methane levels in the plumes are higher than non-biological chemistry alone seems to account for. One explanation is microbes producing it. Methanogens, bacteria that eat hydrogen and carbon dioxide and exhale methane, exactly the way some of the oldest life on Earth works. That explanation hasn't been confirmed. It also hasn't been ruled out. Europa is quieter, but arguably bigger. Its ocean might be 60 to 150 kilometers deep. It contains more liquid water than every ocean on Earth combined. In a moon. NASA's Europa Clipper launched in October 2024. It will arrive in 2030, 49 planned flybys. We will know more. If you were somehow swimming in Enceladus's ocean right now, pitch black, near freezing, 1/10 Earth gravity, the faint chemical signature of vents in the distance, you would be in an environment that on Earth supports life. That's not a metaphor. That's the point. Number 3, the rock that proves it can happen. Here's something that doesn't get taught in school enough. A meteorite from Mars has already landed on Earth. We've found it in Antarctica. We have it. It's called ALH84001. It's sitting in a lab. The transfer happened. Mars to Earth rock delivery is not a theory. It's a documented fact, and it's not a rare event. Models suggest that roughly 1 billion Mars rocks were ejected during the early solar system at temperatures low enough, under 100 degrees Celsius, that anything living inside them could have survived the launch. Some fraction of those rocks ended up on Earth. Some fraction of Earth rocks ended up on Mars. The postal service between planets has been running for 4 billion years. The question is whether anything can survive the trip. And this is where biology gets genuinely unsettling. There's a bacterium called Deinococcus radiodurans. It can survive 1.5 million rads of radiation. For context, 500 rads kills a human. It doesn't just survive radiation, it repairs its own DNA in real time after damage that would permanently destroy any other known organism. It's been called the world's most radiation-resistant life form, and it is a real thing that exists on Earth right now. In an experiment that ran from 2015 to 2018, dried bacterial aggregates, just half a millimeter thick, no rock shielding, survived on the exterior of the International Space Station for 3 years in open space. Vacuum, temperature swings, cosmic radiation, UV. 3 years. The trip from Mars to Earth at 10 kilometers per second takes about 9 months. Do the math. In 1969, a meteorite fell in Murchison, Australia. When scientists analyzed it, they found over 90 different amino acids. 19 of them are used by life on Earth. 70 plus of them are not found in Earth life at all. Life's raw ingredients aren't rare. They fall from the sky. The technical name for this is panspermia, the idea that life, or at least its chemistry, can hitch rides between worlds. It used to be considered fringe science. It's not anymore. The hardware works, the biology can survive. A 2025 study calculated that Europa's ocean may have received somewhere between 10 to the 23rd and 10 to the 24th Earth dust particles over its lifetime, particles that could, theoretically, include viable organisms launched from Earth. Our biology may have already arrived somewhere. We just don't know if it survived landing. The proven part, Mars-Earth rock transfer, is real. Bacteria can survive the conditions. The unproven part, whether anything has actually made an interstellar trip and taken root, that gap is smaller than it used to be. Number 4, 3 visitors from another star. Before October 2017, the answer to the question, how many confirmed objects from other star systems have passed through our solar system, was 0. In all of human history, 0. Then we found one. Then another. Then a third arrived in July 2025. 3 in 8 years. The first was Oumuamua. It means scout in Hawaiian. We spotted it leaving, already past the sun, already accelerating away. Cigar-shaped or maybe flat like a pancake depending on how you model the light curve. About 400 meters long and 40 meters wide. Extreme proportions, nothing like that in our solar system. No coma, no tail, no outgassing. And as it left, it accelerated faster than gravity alone explained, not by a little. By a measurable, undeniable amount. We watched it happen, and we still can't fully explain it. The leading natural explanations, a hydrogen iceberg sublimating invisibly, a fragment of a nitrogen ice planet, a porous dust aggregate, each have problems. None have been confirmed. We observed it for 2 months, and then it was gone, and we will never see it again. The second, in 2019, was a comet. Normal water ice, normal coma. Completely unremarkable, and that's actually interesting, because it means interstellar comets are out there and they look like our comets. The galaxy's chemistry resembles ours. That's a data point. The third arrived July 1st, 2025, and it's the most scientifically valuable of the 3. 3i Atlas, about 20 kilometers across and twice the height of Mount Everest, traveling at 58 kilometers per second, 208,000 kilometers per hour. Retrograde orbit, meaning it's going backwards relative to the plane of the solar system. It passed through, rounded the sun in late October, and left. What made it valuable is that it talked. Spectroscopy, essentially reading the light bouncing off it, revealed heavy water rich in deuterium, a signature of forming in an extremely cold environment far from whatever star it came from. Follow-up observations picked up complex organic molecules, carbon monoxide, carbon dioxide, cyanide compounds, a full chemistry profile, a postcard from another star system written in molecular fingerprints. Scientists confirmed it's a natural comet. That's the consensus. What it carried, organics, water, chemistry from somewhere else entirely, is now documented fact. Interstellar objects are seeding our solar system with the raw materials of other stars. And starting now, with better telescopes coming online, we should detect roughly one per year. Whatever the next 100 look like, we'll be watching. Number 5. The signal that took 18 months to explain. August 15th, 1977. A radio telescope in Ohio is scanning the sky. A researcher named Jerry Eman is reviewing the data printout, and this was done on paper, and he sees a signal so strong, so precisely on the hydrogen frequency, so perfectly shaped like what a transmission from a fixed point in deep space would look like as Earth rotates past it, that he circles it in red pen and writes one word in the margin. Wow. The signal lasted 72 seconds, 30 times background noise, exactly the right frequency, 1,420 megahertz, the hydrogen line, the frequency SETI had been targeting for years because it's so fundamental that any civilization would know it. Never detected again. 47 years of follow-up observations, nothing. It remains unexplained. Then, in 2019, a different telescope picked up something that made serious researchers stop breathing for a moment. A narrowband signal at 982 megahertz coming from the direction of Proxima Centauri, the nearest star to our sun, the one with a confirmed planet in the habitable zone. The signal lasted over 5 hours. It appeared when the telescope pointed at Proxima Centauri and disappeared when it pointed elsewhere. It showed a Doppler frequency drift, the kind you'd expect from a transmitter sitting on a planet orbiting a star. The lead analyst called it on par with the WOW signal. It passed more detection filters than any SETI candidate in history. They named it Breakthrough Listen Candidate 1. It took 18 months to debunk. The culprit was intermodulation, human-made electronics near the telescope generating spurious signals at frequencies that happen to look exactly like an alien transmission, drifting in exactly the right way, aligned with the observation cadence by coincidence. They found dozens of similar artifacts once they knew what to look for. The signal came from Earth. Here's what that means. The pipeline for detecting alien radio signals is now strong enough that it takes 18 months of serious analysis to eliminate a false positive. The tools are real. The search is active. China's fast telescope, 500 meters in diameter, the largest radio dish on the planet, is scanning the sky right now. Breakthrough. Listen has surveyed over 1 million stars. AI pipelines are combing through terabytes of data every hour. We may have already received a real signal and filed it under noise. We genuinely don't know. Number 6. The planet where scientists are actively fighting about life right now. 124 light-years away, there is a planet called K218b. If you drove there at highway speed, it would take roughly 1.4 trillion years, about 100 times the age of the universe. And right now, in real time, 2 groups of scientists are in an argument about whether it has life on it. The planet is a sub-Neptune, bigger than Earth, smaller than Neptune, sitting in its star's habitable zone. The working hypothesis is that it's a Hycean world, a global ocean under a thick hydrogen atmosphere. No land, just water and sky. Which matters because on a planet like that, the biosignature you'd look for isn't oxygen. It's dimethyl sulfide, a gas that on Earth is produced almost exclusively by marine phytoplankton, tiny ocean organisms. Their total biomass is less than 1/billionth of Earth's mass, but they produce enough of this gas that it's detectable from space. In April 2025, a Cambridge team reported 3 sigma evidence for dimethyl sulfide in K218b's atmosphere. 3 sigma means there's roughly a 1 in 300 chance the signal is noise. In physics, you need 5 sigma to claim a discovery. In astrobiology, 3 sigma is the strongest result anyone has ever reported for a potential biosignature on another world. The press release called it the strongest evidence yet that life may exist outside our solar system. Within days, other teams were in the data. Johns Hopkins ran independent analysis and found that 87.5% of their retrieval attempts didn't replicate the signal. The result depended entirely on one specific way of binning the data out of 8 possible methods. NASA's Jet Propulsion Laboratory published its own analysis. No conclusive evidence. The entire controversy is technically about data processing methodology. One binning method out of 8. That's the battlefield. There's a wrinkle that cuts both ways. Lab experiments have shown that dimethyl sulfide can be produced without biology. UV light hitting a simulated hydrogen-rich atmosphere generates it abiotically. The gas has also been detected in comets and interstellar clouds. So even if the signal is real, it doesn't automatically mean life. But here's the thing, on Earth we only know of one process that produces it in any meaningful quantity. That process is life. The detection was based on fewer than 8 transit observations. More are coming. The answer, whatever it is, will probably arrive within a few years. Everything so far has been about whether we can find them. The next 4 are about what happens if they found us first, or if they've been watching all along. Number 7. The statistical proof that if they exist, they're ancient. Forget everything you think you know about what first contact would look like. Forget the movie where the alien ship parks over a city and a ramp comes down and something vaguely humanoid walks out and starts talking. The math says that's almost certainly not what contact looks like. Here's why. In 2020, 3 astrophysicists at Columbia University worked through a statistical problem. If there are civilizations out there with different lifespans, some short-lived like us, some that have been around for millions or billions of years, which ones are you most likely to actually make contact with? The answer is deeply uncomfortable. You are far more likely to contact an older civilization, not because older ones are more numerous, they might not be, but because a civilization that's been transmitting for 1 million years has had 1 million years to leave signals for you to find. A civilization that existed for 50 years and then went silent is almost impossible to detect. The longer something has been broadcasting or building or modifying its environment, the bigger its footprint, the higher the probability you run into it. The researchers called it contact inequality, the same reason that wealth surveys are dominated by billionaires even when billionaires are rare. The math suggests our first contact would most likely be with something that has had thousands, maybe millions, maybe billions of years of development over us. Carl Sagan and Stephen Hawking both said this intuitively. The paper put numbers on it. Hawking's read on this was not optimistic. More advanced, he argued, probably means more dangerous. He compared it to what happened when technologically superior civilizations encountered less advanced ones throughout human history. The record is not good. The caveat, the model assumes civilizations follow an exponential lifetime distribution. That's a reasonable guess. It's still a guess. But the direction of the conclusion is hard to escape. If they exist and we find them, we are almost certainly not meeting equals. Number 8, the reason the silence might be the loudest signal of all. Here's the problem that doesn't go away. If there are potentially millions of civilizations out there, some of them billions of years old, and the Milky Way is 13 billion years old, then any civilization with even a fraction of our current ambition could have colonized the entire galaxy long before humans existed. At 1/10 the speed of light, fast but not impossible in principle, you could see the whole Milky Way in 10 million years. 10 million years is 1.3 thousand times before the present moment. Going back, the galaxy is old, really old, and we see nothing. No signals, no megastructures, no visiting fleets, no alien biology in our fossil record. We call this the Fermi paradox, and it is genuinely one of the most unsettling open questions in science. There's a new piece to it from 2024. A study looked at the role of plate tectonics, the movement of Earth's crust, in producing complex life. Plate tectonic cycles, carbon and nutrients. Without it, you probably don't get the kind of sustained, diverse biosphere that leads to intelligence. And it turns out that having both the right balance of ocean and continent and having plate tectonics run for over 500 million years may be extraordinarily rare. The fraction of habitable planets that tick both boxes could be as low as 3 in 100,000. If that's right, the Fermi paradox solves itself without anyone having to blow themselves up. Complex life is just vanishingly unlikely, and Earth got extraordinarily lucky. But here's the version that's harder to shake. Maybe the reason we hear nothing is because broadcasting is dangerous. A hypothesis called the dark forest says that every civilization in the galaxy eventually reaches the same conclusion. Revealing your existence is a survival risk. Any older, more powerful civilization that detects you might destroy you before you can threaten them. The rational move is silence. Complete, permanent silence. The galaxy could be full of civilizations that have each independently decided never to speak. The silence isn't emptiness, it's fear. Oxford researchers ran a Monte Carlo analysis where they basically threw realistic uncertainty into the Drake equation and simulated it millions of times, and found about a 30% chance we are alone in the entire observable universe, and about a 53% chance we are alone in just the Milky Way. Those are not small numbers, but flip it the other way. Across 2 times 10 to the 22nd stars in the observable universe, for us to be unique, the odds of any habitable planet producing a civilization would have to be worse than 1 in 10 billion trillion. 1 in 10 to the 22nd. That number is so small it barely has meaning. Most scientists find it hard to believe we're that special. The silence remains. But silence is evidence too. Number 9. The structures we're actually looking for. In 1960, physicist Freeman Dyson asked a question that sounds like science fiction but isn't. If a civilization has been around long enough and needs more energy, what do they build? His answer: a structure around their star. Capture everything. All of it. Every photon the star emits, redirected into usable power. The waste heat from a structure like that would radiate into space at around 300 Kelvin. Mid-infrared, detectable, distinguishable from a normal star if you know what to look for. This is called a Dyson sphere, though modern versions are more like a swarm of collectors than a single shell. A solid shell around the sun would require dismantling every planet in the solar system, and it would be mechanically unstable. A swarm of orbital platforms is actually theoretically buildable by a sufficiently advanced civilization. In Nikolai Kardashev's 1964 framework, a civilization that has done this is called a Type 2. It has fully harnessed its star. Humanity, for comparison, is currently around 0.73 on that scale. In 2024, astronomers searched 5 million stars using multiple sky survey datasets and found 7 that glow wrong in the infrared. 7 M-dwarf stars, red dwarfs, smaller and dimmer than our sun, within 900 light-years, all producing more mid-infrared radiation than their stellar type should generate. The temperatures of the excess heat between 100 and 600 Kelvin, consistent with Dyson swarm waste heat. One of the 7 was later explained by a background galaxy contaminating the data. 5 remain. Astronomers followed up with radio telescopes. No artificial signals. Which is consistent. A civilization that doesn't want to be found wouldn't broadcast. It's not confirmation. It's not refutation. It's 5 stars with anomalous heat signatures and no natural explanation confirmed. Then there's Tabby's star. Irregular dimming of up to 22% of its brightness. A transiting planet blocks less than 1%. The leading explanation is a cloud of disintegrating cometary material. That explanation is not confirmed. The dimming is still happening. The star is still behaving in a way that has no fully settled natural explanation. To be clear, the Dyson sphere interpretation is speculative. These are real anomalies without confirmed explanations, not confirmed megastructures. Both things can be true. We're looking. We have candidates. We don't have answers yet. Number 10, the math that makes all of this statistically reasonable. In 1961, astronomer Frank Drake wrote an equation on a chalkboard to set the agenda for a meeting about the search for extraterrestrial intelligence. It became the second most famous equation in science after E equals mc squared. It's called the Drake equation, and it estimates the number of civilizations in the Milky Way we could theoretically make contact with right now. The range of answers, depending on which values you plug in, runs from 0.0000000001, essentially alone in the galaxy, probably alone in the universe, to 15,600,000 active communicating civilizations in the Milky Way right now. Drake himself thought the answer was around 10,000. The two variables we've actually nailed down since 1961, how fast stars form and how common planets are. The Kepler telescope basically proved that planets are everywhere. Most stars have them. Everything after that, how often life starts, how often it becomes complex, how often it becomes intelligent, how long it lasts, we're still guessing. We have one data point, us. That's the entire sample size. A 2024 revision added plate tectonics to the equation. That alone drastically shrinks the optimistic end of the range. Another paper added population dynamics, the argument that intelligent species may inherently tend toward reproduction decline as they develop, a kind of civilizational demographic collapse that applies to any species smart enough to stop breeding at replacement rate. Each edition compresses the estimate further, but here's the number that doesn't compress. Adam Frank at the University of Rochester asked a different question. Not how many civilizations exist right now, but how many have ever existed across the entire history of the observable universe, across 2 times 10 to the 22nd stars. His answer, for us to be the only ones ever across all of that, the probability of a civilization emerging on any given habitable planet would have to be worse than 1 in 10 to the 22nd. 1 in 10 billion trillion. He said before that result, you'd be considered a pessimist if you put the odds at 1 in a trillion. But even 1 in a trillion means civilization has happened 10 billion other times in cosmic history. Here's where we actually stand. Microbial life somewhere in the universe. Near consensus among scientists. Microbial life in our own solar system, right now, in an ocean we know exists. Considered plausible by the majority of astrobiologists. A biosignature gas on a planet 124 light-years away, 3 sigma evidence actively contested, intelligent life existing somewhere in the universe. 58% of experts say probably yes. Direct contact unknown. We've been a radio broadcasting civilization for about 100 years. Our signal bubble covers roughly 15,000 stars. There are 400 billion in the Milky Way. We've barely introduced ourselves.